Now we're going to see circular openings and Rayleigh criteria. We have now a circular opening as opposed to the single slit that we had. Here we have could be the screen or whatever we have. If we grab with a single slit, here the intensity of the light, and here could be theta or could be x. We saw this pattern with maximums with both decaying maximums. So it is decaying. This would be the pattern that we would see with a single slit. It's quite similar for a circular opening. So here now we would have a circular opening. Could be a telescope, could be the human pupil. This is the pattern that we would see. Now remember that for the single slit we have that theta is equal to lambda times n divided by the distance of the opening. Let me call it A. Could be A or could be D, whatever. So it is A. If we have two circular openings, so we have two sources of light, could be the headlights of a car. So now we have two circular openings. We could see in each one this diffraction pattern. So we want to know what is the minimum distance at which the two sources could be, from which we can distinguish that there are two sources. That is, if they are very close together, we will only see one diffraction pattern. Could be a little bit mixed up, but we will see that if the diffraction pattern is coming from only one source. We want to see what is the minimum distance. So this minimum distance, or like this, what is the minimum distance in which we will distinguish that the light is coming from two sources. That would be, here we have the diffraction pattern for one. This would be the diffraction pattern. This would be theta 0, this would be theta 1, theta 2. This for one pattern, and this for one opening, and this for the other opening. The minimum distance is when this theta 0 of the second opening be at the position of the first or of the first order of theta 1 of the first aperture. So when this be here, so we will have something like this. This is the first aperture pattern, and this would be here. This would be the minimum distance. Now we could measure it in angular distance or in normal distance, not angular distance. So the angular distance would be this, just n lambda over a n. You will think that is 1 because we're taking the first order. Now it is not quite 1 because we are not taking the symmetry of the line, is not exactly, so it is actually 1.22. So this would be the angular distance, and this is called Rayleigh criteria. Now if we want to know not the angular distance but this distance, as an example, let's suppose that we have a car. The headlights are 3 meters apart. The human pupil is 5 millimeters. Actually, could be less, but let's do with that. And we are shining yellow light that has 600 nanometers of wavelength. We want to know what is the minimum. Now we want to know what is now the distance from here. Here we are. Here is the car with the two light sources that are 3 meters apart. Now we want to know what is the minimum distance at which we will distinguish that at 3 meters there are 2 diffraction patterns, or that there are 2 sources of light. I think that this is quite complex, so I will ask you certainly that if you think you can do it, stop the video now and you can continue to see we have the same result, but well, anyway, I will continue here. So we have the circular opening here, we have the screen here, this distance, the horizontal distance is D, we see this pattern, could be this, actually let me put the, if you want, here, this is D. This is the distance between, could be between one source and the other, so 3 meters here, because here we have one light and another light, and these are like these sources of light, but well, I think that I'm using the word source for 2 different things. Look, the aperture is here and it is the pupil, that this is 5 millimeters on diameter, and here we have the lights that we are seeing, they are 3 meters apart. We want to know what is this distance. So first we will use the small angular approximation. Remember that here is not quite theta, it is sine theta, but because for the small angular approximation sine theta is equal to theta, we could use it as that. So here we have what is the sine of theta, sine of this angle is D, let me call this distance A, could be, or well, 3 meters, 3 meters, over the hypotenuse, I will say over the hypotenuse. Alright, maybe we could use tangent. So tangent of theta, actually, let me do it tangent of theta 2. So this would be theta 2. So tangent of theta 2 is 1.5 meters divided by D. So this, again, for the small angular approximation, the tangent of theta is the same as theta. So actually theta is, tangent of theta over 2. Tangent of theta over 2, sorry, because I'm just taking this. So I have that theta over 2 is 1.5 meters over D. So I have that theta is 3 over D. The same as for the small angular approximation now. Now we have theta is 3 over D. We could try to find the sine, but we know that by the small angular approximation, sine of theta is equal to theta. So we would plug here 3 over D is equal to 1.22 times the wavelength, that is 600 nanometers, nanometers, divided by 8, that is the aperture of the pupil, so it is 5 millimeters. And now we just need to find D. I will leave you with the argument. So this is how we can know the angular distance from the sources, the minimum distance at which we can distinguish them, and the minimum distance from the given 2 sources with a fixed distance, which is the minimum distance from those sources to those at which we can distinguish that 2 sources are emitting the light.